The universe is not just big, it contains structures so huge they stretch across billions of light years, dwarfing entire galaxies and rewriting what we thought size even means. From huge galaxy filaments to superclusters holding thousands of galaxies together, today we're counting down the 12 largest known objects ever discovered in the universe, where every entry challenges the limits of cosmic scale. The universe is far bigger than we expected. The universe looks simple when you first see it from Earth. You look up at the night sky and you see stars, and it feels like space is full of small points of light spread out in a quiet, dark sky. But what we see with our eyes is only a tiny piece of a much larger system, and when scientists began to measure space in a serious way, they found that everything is on a scale that is hard to imagine at first. The part of the universe we can observe, called the observable universe, is already extremely large. It stretches about 93 billion light-years across from one side to the other. A light-year is the distance light travels in 1 year, and light moves fast beyond anything on Earth. Even at that speed, it takes billions of years to cross the biggest parts of space. So when we talk about size in the universe, we are not talking about kilometers or miles. We are talking about distances so large that even light needs millions or billions of years to move across them. When scientists say something is the largest in the universe, they are not talking about just one simple idea. There are different ways to measure size, and each one tells a different story. Some objects are large in physical width, meaning how far they stretch from one side to another. Some are large in mass, meaning how much matter they contain. Some are large in influence, meaning how far their gravity can affect other objects around them. In space, all of these can be different for the same object. A galaxy might be large because it spreads across hundreds of thousands of light years and contains billions of stars. A black hole might be large because its mass is so heavy that it bends space itself. A cluster of galaxies might be large because it holds hundreds or even thousands of galaxies together with gravity. A supercluster might be large because it stretches across hundreds of millions of light years, connecting groups of galaxies into massive networks. And beyond that, there are cosmic filaments and walls, huge thread-like structures that connect everything together like a web across space. Between those structures are voids, empty regions so large that entire galaxies are missing inside them. To understand how we discovered these things, it helps to know how astronomy changed over time. At first, humans could only use simple optical telescopes. These telescopes collected visible light, and they showed that the Milky Way was not alone. They revealed other galaxies, but they looked like small, blurry patches. At that stage, the universe still looked somewhat simple, like a collection of isolated islands in space. Later, scientists started measuring how fast galaxies move. This is called redshift, and it happens because light stretches as objects move away from us. By studying redshift, astronomers could estimate how far galaxies are and how the universe is expanding. This changed everything because it turned space from a static picture into something that is growing and stretching. Then came large galaxy surveys, like the Sloan Digital Sky Survey, which mapped millions of galaxies in detail. Instead of looking at just a few objects, scientists suddenly had massive maps of the universe. These maps showed that galaxies are not spread evenly. They form patterns like long chains, walls, and empty gaps. At the same time, radio astronomy opened another window into space. Some of the largest structures do not show up well in visible light, but they can be detected using radio waves or X-rays. This allowed scientists to find massive jets from black holes, giant clusters of hot gas, and hidden structures behind dust and other galaxies. As instruments improved, one thing kept happening over and over again. Structures that were once thought to be huge turned out to be part of even larger systems. A galaxy was once the biggest known structure, then clusters became the biggest, then superclusters, and then even larger cosmic walls and filaments were found. Every time the tools improved, the universe looked bigger than before. This is why the idea of largest things in the universe is always changing. It is not a fixed list. It depends on what we can detect, how far we can see, and what kind of light or signal we are using. Some structures are so large and so spread out that they are still being mapped today, and in some cases scientists are still debating if they are real or just patterns caused by how we collect data. IC 1101, the largest known galaxy. IC 1101 is one of those objects in space that forces you to rethink what a galaxy even is, because when you first hear galaxy, you might think of something like the Milky Way, a huge spiral system with bright arms, dust lanes and a glowing center. But IC 1101 is not like that at all. It is far larger, far older in structure, and far more spread out than most galaxies we normally talk about. And it sits so far away that even its full shape is hard to capture clearly. Yet what scientists have measured so far already places it at the very top of known galaxy sizes. This galaxy was first discovered in 1790 by William Herschel, who was scanning the sky with one of the early powerful telescopes of his time. And like many discoveries from that period, it was not understood in full detail at first, because at that time galaxies were not even clearly known as separate systems outside the Milky Way. So IC 1101 would have appeared as just a faint glowing patch in the sky, something that looked like a soft cloud of light rather than a structured system of billions of stars. And it would take more than a century of better instruments and deeper surveys before scientists could properly place it in the correct category and understand that it was not just large, but extreme, even by galaxy standards. Over time, with better telescopes and better methods of measuring distance, IC 1101 was reclassified as an extreme supergiant elliptical galaxy, which already tells a lot about its nature, because elliptical galaxies are not like spiral galaxies with clear arms and rotating patterns. Instead, they are more like large, smooth, rounded collections of stars, where motion is more random and less structured. And in the case of IC 1101, this structure is stretched to an extreme level, where the galaxy becomes so large and so spread out that its edges are not sharply defined, but instead fade slowly into surrounding space. When scientists estimate the size of IC 1101, they are dealing with numbers that are difficult to visualize in normal terms, because its diameter is around 6 million light-years across, although this number can vary depending on how the outer regions are defined, since the galaxy does not have a hard boundary like a planet or even a smaller galaxy, and this alone makes it many times larger than the Milky Way, which is only about 100,000 light-years across, meaning IC 1101 could fit dozens of Milky Way galaxies side by side across its width and still have space left in its outer regions. Inside this massive structure, scientists estimate that there could be around 100 trillion stars, which is a number so large that it is hard to connect to anything familiar, because even if you imagine every star as a sun like our own, the total count is far beyond anything we can mentally track. And these stars are not packed tightly like in smaller galaxies. Instead, they are spread across a vast, thin structure where distances between stars in some regions can be far greater than what we see in denser parts of galaxies like the Milky Way's central regions. IC 1101 is located in a galaxy cluster known as Abell 2029, which is itself a massive structure filled with many galaxies bound together by gravity. And this environment plays a major role in how IC 1101 formed, because galaxies in clusters do not stay isolated for long periods of time. They interact, they pass through each other, and in many cases they merge, and over billions of years, these repeated mergers can build a single galaxy that grows larger and larger, absorbing the stars and matter of other galaxies until it becomes a dominant central object in the cluster, which is exactly what scientists believe happened in the case of IC 1101. The structure of IC 1101 is one of its most important features, because instead of having clear spiral arms or a sharply defined shape, it has a very diffuse outer halo, which means that the outer regions are spread out and faint, gradually blending into the surrounding space rather than ending suddenly. And this halo contains stars that are loosely bound, moving under the combined gravity of the galaxy and the cluster it sits in. And this gives the entire system a soft, extended appearance that can stretch across millions of light-years without a clear edge. At the centre of IC 1101, there is an enormous bulge, which is the dense core region where a large number of stars are packed more closely together. And this central region is thought to contain a supermassive black hole, as is common in large elliptical galaxies, although the exact properties of this black hole are difficult to measure directly. And what makes this even more interesting is that the central bulge is not just large, it is also very bright in comparison to the outer regions, meaning most of the galaxy's visible light comes from this inner core, while the outer halo remains faint and spread out. The formation of IC 1101 is strongly linked to repeated galaxy mergers, which is a process where smaller galaxies collide and slowly combine over time. And in a dense environment like a galaxy cluster, this process happens more often, because galaxies are close enough to interact gravitationally, and each merger adds more stars, more gas and more dark matter into a single growing system. And over billions of years, these repeated events can build a galaxy far larger than anything formed in isolation, which is why IC 1101 is believed to have grown step by step through a long history of cosmic collisions, rather than forming in a single event. What makes this even more extreme is that IC 1101 is now considered a quiescent galaxy, meaning it is not actively forming new stars at a significant rate. And this is a key point in understanding its current state, because most of its gas, which is needed to form new stars, has already been used up or heated to the point where it cannot easily collapse into new star systems. And without fresh cold gas coming in, star formation slows down or stops entirely, leaving behind a stable but aging population of stars that slowly evolve over time. To understand how scientists measured IC 1101, it is important to know that no single image can give its full size directly. Instead, its properties are measured using a combination of optical imaging and redshift distance calculations, where optical imaging helps map the visible structure of the galaxy, showing how far its light spreads and how bright different regions are, while redshift measurements help determine how far away the galaxy is by studying how its light stretches as the universe expands. And combining these two methods allows astronomers to estimate both its distance and its physical size. In addition to these methods, space telescopes like Hubble have been used to observe the environment around IC 1101, especially the galaxy cluster it belongs to, because understanding the cluster is important for understanding the galaxy itself, since the gravitational environment affects how galaxies move, collide, and grow. And by studying how galaxies are distributed in a Bell 2029, scientists can better understand how IC 1101 reached its current size and why it sits at the centre of such a massive system. The scientific importance of IC 1101 goes beyond just its size, because it shows the upper limits of how large a galaxy can grow through mergers, and it raises important questions about what stops galaxies from growing even larger. Since in theory, more mergers could continue to increase size, but in reality, there are limits based on available material, gravitational stability, and the structure of the surrounding cluster, meaning IC 1101 may represent a kind of natural boundary for galaxy growth under current cosmic conditions. Another important aspect is how IC 1101 helps scientists understand why some galaxies stop forming stars. Because once a galaxy becomes this large and massive, it can heat up surrounding gas through energetic processes linked to its central black hole and past merger activity. And this heated gas cannot easily cool down to form new stars, which leads to a slow decline in star formation, leaving the galaxy in a stable but inactive state, where most of its stars are old and no major new star formation is taking place. IC 1101 also challenges earlier ideas about galaxy classification, because it does not fit neatly into simple categories like spiral or normal elliptical galaxies. Instead, it exists at an extreme end of the elliptical type, where size, mass, and structure push the limits of what was expected when astronomers first started classifying galaxies. And this forces scientists to refine their models of how galaxies evolve in dense environments. Even though IC 1101 is one object, it is also a record of billions of years of cosmic history, because every merger it experienced left behind stars from smaller galaxies and each layer of its outer halo contains traces of past collisions, meaning that when scientists study its structure, they are essentially reading a long timeline of galaxy formation written across space, not in words, but in the distribution of stars and the shape of its extended glow across millions of light years. Alcyoneus, largest radio galaxy ever found. Another largest thing ever discovered in the universe is Alcyoneus. Largest radio galaxy ever found. Alcyoneus discovery was not first seen as a bright galaxy in a telescope image like many famous space objects. Instead, it was found through radio waves, which are invisible to human eyes and only become clear when captured by special instruments built to detect low-frequency signals coming from deep space. And this already sets the stage for something unusual, because radio astronomy often reveals objects that are hidden, faint, or spread out across distances so large that normal optical telescopes miss them completely. The discovery of Alcyoneus happened in 2022 during a large survey using the LOFAR radio telescope, which is a system made of many linked antennas spread across Europe, working together as one giant virtual telescope. And its job is not to take pictures in visible light, but to map radio signals from space with extreme sensitivity. And while scientists were studying data from this survey, they began to notice a structure that did not fit into normal patterns seen in radio galaxies, because instead of a compact or moderately sized radio source, they found something that stretched across a distance so large that it immediately stood out from everything else in the data set. At first, this kind of detection is not instantly labelled as a new record-breaking object, because radio astronomy data can be complex, and signals can appear stretched or distorted due to distance, angle, or surrounding space conditions. So scientists carefully rechecked the source, confirmed the structure, and then slowly realized that they were not looking at a normal radio galaxy, but something far larger, something that extended well beyond expected limits for galaxy-scale radio emissions. And this is where Alcyoneus begins to separate itself from everything previously known. When its full structure was measured, scientists estimated that Alcyoneus stretches around 16 million light-years in length, when including its radio jets and lobes, which makes it one of the largest known single structures linked to a galaxy. And to understand how large this really is, it helps to compare it with something familiar like the Milky Way, which is only about 100,000 light-years across, meaning Alcyoneus is not just larger, it is hundreds of times larger than a normal galaxy, and even stretches across distances that go far beyond entire galaxy groups, making it a structure that connects the small scale of a single galaxy to the vast empty spaces between galaxies. But Alcyoneus is not large in the way a galaxy like IC 1101 is large, because IC 1101 is a massive collection of stars packed into a single gravitational system, while Alcyoneus is defined mainly by its radio emission structure, which comes from energetic jets fired out from the center of its host galaxy. And these jets are not made of stars or solid matter, but instead are made of charged particles moving at extremely high speeds, guided by magnetic fields and powered by a central supermassive black hole, and these jets travel far beyond the visible boundaries of the galaxy itself. The key structure behind Alcyoneus is its active galactic nucleus, often shortened to AGN, which is the central region of a galaxy where a supermassive black hole is actively pulling in matter from its surroundings. And as this matter falls inward, it heats up and forms a rotating disk of extremely hot gas and dust. And in many cases, this process does not only pull matter inward, but also pushes energy outward in the form of twin jets that shoot in opposite directions from the center of the galaxy, and these jets can travel vast distances into space. In Alcyoneus, these jets are not small or contained close to the galaxy. Instead, they extend far beyond the host galaxy itself, stretching into intergalactic space, where the density of matter is extremely low. And as they move outward, they create large radio-emitting regions called radio lobes, which are basically huge cloud-like zones filled with energetic particles that glow strongly in radio wavelengths. And these lobes are what make Alcyoneus visible in radio surveys even when the host galaxy itself may not appear especially remarkable in optical light. The host galaxy of Alcyoneus sits at the center of this system, acting as the source point for all this energy. And while the galaxy itself is not the largest known in terms of stars or mass, its central black hole plays a key role in shaping the massive structure around it, because everything we see in Alcyoneus at large scale is driven by energy released from the region near this black hole. And this energy is converted into motion, heat and radiation that travels outward in opposite directions. As these jets travel outward, they do not move through empty space in a simple straight line without change, because space is not completely empty, and even in intergalactic regions there is very thin gas and plasma spread across vast distances. And when the jets from Alcyoneus move through this environment, they interact with it, pushing against it, heating it, and losing energy over time. But in the case of Alcyoneus, these jets have managed to maintain structure and coherence over a distance that is extremely unusual, which is part of what makes this object so important to study. The measurement of 16 million light-years is not a simple direct measurement like measuring a physical object in a lab. Instead, it is built from mapping the extent of radio emission detected by LOFAR and combining that with distance estimates based on redshift data from the host galaxy, which tells scientists how far away the system is based on how much its light has stretched due to the expansion of the universe. And once the distance is known, the observed angular size of the radio lobes can be converted into a physical scale, giving a full estimate of how large the structure really is in space. What makes this measurement especially striking is that the radio structure of Alcyoneus is not just large in one direction, but extends in two opposite directions from the central galaxy, forming a kind of long, stretched system that can span millions of light-years on each side. And this is not a static object, because these jets are formed over long periods of time. Meaning, what we see is not a single moment, but the result of continuous energy output from the central black hole over millions of years, slowly building up the enormous structure we observe today. Why it is so large, how it forms, and what it changes in astronomy. The structure of Alcyoneus can be understood as a combination of three main parts working together, even though they are not separate objects in space, but connected regions of one system, starting with the central host galaxy, where the supermassive black hole sits, then the twin jets that carry energy outward in narrow beams, and finally the radio lobes that form at the ends, where these jets slow down and spread out into large diffuse regions. And each of these parts plays a role in building the full size of the system. Alcyoneus becomes even more interesting once you move past the discovery and the basic size, because the real question is not just how big it is, but why it is this big in the first place, since most radio galaxies do not reach anything close to this scale. And even powerful active galaxies tend to have jets that slow down, break apart, or fade much earlier. Yet Alcyoneus continues far beyond what scientists expected, and that forces a deeper look into how these systems actually grow over time, and what conditions allow them to stretch across such extreme distances. To understand why Alcyoneus is classified as the largest radio galaxy ever found, you have to focus on the radio lobes, because these are the outermost parts of the system and the regions that define its true scale. And in this case, the radio lobes extend so far from the central galaxy that they exceed the size of entire galaxy groups, meaning that the energy produced at the center is not just affecting the host galaxy, but is being pushed far into intergalactic space, where galaxies are separated by huge empty regions. And even in those low-density areas, the structure remains visible in radio wavelengths. These radio lobes are not solid structures. They are made of extremely thin plasma, which is a gas made of charged particles like electrons and ions. And this plasma is energized by the jets coming from the active galactic nucleus. And when those jets reach the outer regions, they slow down and spread out, creating large balloon-like regions filled with energetic particles and magnetic fields. And even though the density of this material is extremely low compared to anything on Earth, the scale is so large that the total volume becomes enormous. And this is what allows Alcyoneus to be detected as a giant radio structure across millions of light years. The reason these lobes can grow so large in Alcyoneus is closely linked to how the jets behave as they move outward, because in many radio galaxies, jets lose energy quickly when they collide with dense gas or encounter turbulent regions in space, which causes them to bend, break, or fade. But in the case of Alcyoneus, scientists believe the surrounding environment plays a major role, because the galaxy sits in a region of space that may have unusually low density, meaning there is less material to slow the jets down, allowing them to travel farther before dispersing their energy. This is where the formation mechanism becomes important, because everything starts at the supermassive black hole in the center of the host galaxy, which is actively feeding on surrounding matter, and as gas and dust fall toward the black hole, they form a spinning accretion disk that becomes extremely hot due to friction and compression. And this process releases huge amounts of energy, some of which is radiated away as light, while another part is redirected along the black hole's magnetic field lines, forming two powerful jets that shoot outward from the poles of the system at near relativistic speeds. These jets are not random or uncontrolled. They are shaped by magnetic fields that guide their direction, keeping them narrow and focused over long distances. And as long as the black hole continues to feed, the jets can remain active for millions of years, constantly injecting energy into space and gradually building the large radio structure we see today. And in Alcyoneus, this process has been active long enough and stable enough to create a system that extends far beyond typical radio galaxy limits. Another important factor in its formation is time, because these structures do not form quickly. They require long periods of continuous activity, and the size of the radio lobes is directly linked to how long the jets have been active, meaning that Alcyoneus is not just powered by a strong black hole, but also by a long-lasting one, capable of sustaining jet activity over extended cosmic timescales without major interruptions. And this long duration allows the jets to push energy farther and farther into space, until they reach distances measured in millions of light years. But even with powerful jets and long activity periods, not every environment would allow a structure like this to form, because the surrounding intergalactic medium plays a key role in shaping the final size. Since if the surrounding space is dense, jets lose energy quickly. But if the space is more empty, jets can travel farther with less resistance. And in the case of Alcyoneus, evidence suggests that the galaxy may be located in a relatively low-density region compared to other radio galaxies, which means the jets face less opposition as they expand outward, allowing them to maintain structure over extreme distances. This combination of a powerful central black hole, long-lasting jet activity, and a favorable surrounding environment creates the conditions needed for a structure like Alcyoneus to exist. And when all of these factors align, the result is not just a large galaxy, but a cosmic-scale energy system that extends far beyond what was previously thought possible for a single galactic source. The scientific importance of Alcyoneus becomes clear when you look at what it reveals about jet propagation, because before its discovery, models of radio galaxy jets suggested certain limits on how far these structures could remain stable, based on energy loss, interaction with surrounding gas and magnetic field weakening. But Alcyoneus pushes beyond those expectations, showing that under the right conditions, jets can travel much farther than previously modelled, and this means that existing theories about jet lifetime, stability, and energy distribution need to be adjusted to account for these extreme cases. It also raises questions about how common these giant radio galaxies might actually be, because Alcyoneus may not be a completely unique object, but rather one of the few that has been detected so far due to limitations in current surveys, since many similar structures could exist but remain undetected because their radio signals are too faint, too spread out, or located in regions of space that have not been studied in enough detail. and this suggests that the universe may contain more extreme radio structures than currently catalogued. Another key point is what Alcyonius tells us about the relationship between galaxies and their environments, because it shows that a galaxy is not an isolated system, but part of a much larger environment where intergalactic gas surrounding structures and cosmic voids all play a role in shaping how energy moves through space. And in this case, the environment may be just as important as the black hole itself in determining the final size of the radio structure. The central black hole in Alcyonius does not need to be the largest known black hole for the system to become enormous, because size in this case is not only about mass, but also about efficiency of energy output and how well that energy is transported into space, meaning that even a moderately powerful black hole, if placed in the right environment and active for long enough, can produce a structure that stretches across millions of light years, which is exactly what makes Alcyonius such an important case study. As scientists continue to analyze radio surveys from instruments like LOFAR and future telescopes with even higher sensitivity, Alcyonius serves as a reference point for what extreme radio structures can look like, and it helps refine the search for similar objects that may be hidden in the data, especially in regions of the sky that have not yet been mapped in full detail. And each new discovery like this adds another layer to our understanding of how energy from black holes interacts with the larger scales of the universe. TON 618, one of the largest black holes ever found. TON 618 is one of those space objects that does not reveal its true nature at first glance, because when it was first detected, it did not look like a black hole at all, and it did not appear as a dark object sitting in space either. Instead, it showed up as a very bright, distant source of light, something that looked more like a star in early telescope data, but was far too far away and far too powerful to be a normal star. And this is where its story begins, in a time when astronomers were still trying to understand strange bright points in the sky that did not match known categories. The first detection of TON 618 happened in 1957, during sky surveys that were not originally designed to find black holes, because at that time the idea of supermassive black holes was still not fully developed, and scientists were more focused on cataloguing visible light sources, radio sources, and unusual objects that stood out from normal stars. So when TON 618 appeared in the data, it was recorded as a quasar-like object, meaning a very bright and distant source of energy. But its true nature was not yet fully understood. A quasar is not a simple object like a star or a planet. Instead, it is the extremely bright core of a distant galaxy, where a supermassive black hole is actively pulling in matter at very high speed. And as this matter falls towards the black hole, it heats up due to friction and extreme gravitational pressure, creating a glowing disk of gas and dust that can outshine the entire galaxy around it. And this is why quasars can be seen across billions of light years, even though they are extremely far away, because their energy output is so intense that it becomes visible across cosmic distances. TON 618 was identified as one of these quasars, but what made it stand out was not just its brightness, but its distance and the strength of its energy output. Because as astronomers studied its light more carefully, they realized that it was coming from a region so far away that the light had traveled for billions of years before reaching Earth. Meaning, we are seeing it as it was in the very early universe, not as it exists today. And this already placed it in a special category of extreme cosmic objects. As technology improved and better spectral analysis became available, scientists were able to study the light from TON 618 in more detail. And this is where things became even more interesting, because the light coming from it was not just bright, it was also showing strong signs of being affected by extreme gravitational forces, which suggested that the object producing it was not just large, but far more massive than most known black holes at the time. Over time, using improved measurement techniques based on spectral line broadening, scientists estimated that TON 618 contains a black hole with a mass of around 66 billion times the mass of the Sun, which places it among the most massive black holes ever measured. and this number alone is difficult to fully imagine, because the Sun itself is already extremely massive compared to anything on Earth. And yet this black hole contains a mass equivalent to tens of billions of suns compressed into a single region of space. To understand the scale in another way, the event horizon of Ton 618, which is the boundary around the black hole beyond which nothing can escape, is so large that it would extend well beyond the size of the entire solar system, meaning if you placed it at the center of our own system, it would not just swallow planets, it would stretch far past the orbits of outer planets and into regions of space where comets and distant objects travel, making it not just a point in space, but a massive region of gravitational control that reshapes everything around it. This extreme size places Ton 618 into the category of ultramassive black holes, which are the highest known class of black holes in terms of mass. And these objects are usually found at the centers of large galaxies, where they grow over time by pulling in matter, merging with other black holes, and feeding on surrounding gas and stars. And in the case of Ton 618, the surrounding environment is not just a normal galaxy, but a highly energetic and active region that produces intense radiation across multiple wavelengths. The structure around Ton 618 is dominated by what is known as an accretion disk, which is a spinning disk of gas, dust, and stellar material that is slowly falling into the black hole. And as this material spirals inward, it becomes compressed and heated to extreme temperatures, producing intense light and radiation, especially in ultraviolet and X-ray wavelengths. And this is what makes the quasar so bright, because even though the black hole itself does not emit light, the material falling into it becomes one of the brightest sources in the universe. Around this accretion disk, there is a region of extreme energy output, where radiation pressure, magnetic fields, and gravitational forces interact in complex ways, and this region is not stable in a simple way, because matter is constantly moving inward while energy is constantly being released outward, creating a system that is in constant motion, with material being heated, compressed, and sometimes even ejected in high-speed outflows that can affect the surrounding galaxy on large scales. The brightness of Ton 618 is so extreme that it can outshine entire galaxies, even though it is powered by a single central black hole. And this is one of the most important features of quasars in general, because they show how a relatively small region near a black hole can produce more energy than billions of stars combined, simply through the process of accretion, where gravitational energy is converted into radiation as matter falls inward. What makes Ton 618 especially important is that it is not just bright, but also extremely distant, meaning we are observing it as it existed billions of years ago, at a time when the universe was much younger. And this gives scientists a direct window into early black hole formation, because seeing such a massive object so early in cosmic history raises questions about how black holes can grow to such extreme sizes in such a relatively short time. The host system of Ton 618 is not fully visible in optical light due to its distance and brightness, but it is believed to be a massive galaxy that surrounds the central black hole, providing the material needed to fuel its growth. And over time, as the black hole consumes gas and merges with other systems, it increases in mass, gradually building up to the extreme size we observe today, although the exact details of this growth process are still an active area of research. One of the key reasons Ton 618 appears so extreme is the efficiency of its energy output, because as matter falls into the black hole, a significant portion of its mass is converted into radiation, and this process is far more efficient than nuclear fusion in stars, meaning even small amounts of matter can produce enormous amounts of energy when processed through the accretion disk. And this is what allows quasars like Ton 618 to become some of the brightest objects in the universe. How it was measured, what it changes, and why it breaks expectations. After Ton 618 was identified as a quasar and its extreme brightness was confirmed, the next problem for scientists was not just describing it, but actually measuring what was producing that level of energy. Because at that distance, there is no direct way to see the black hole itself, and even powerful telescopes only capture the light from surrounding matter, not the object hidden at the center. So everything about its size and mass had to be worked out using indirect signals hidden inside the light spectrum. One of the main tools used to understand TON 618 is something called spectral line analysis, which means studying the light from the quasar and breaking it into its component wavelengths. Because when light comes from hot gas moving at extreme speeds, it does not stay uniform. Instead, it shows patterns that stretch and shift depending on how fast the gas is moving, and these shifts become a kind of hidden map of motion around the black hole. In the case of TON 618, the light coming from hydrogen gas near the black hole showed very strong broadening in its emission lines, which means the gas is moving at extremely high speeds in different directions at the same time, some parts moving toward us and some moving away. And this spread in motion is not random. It is directly caused by the gravitational pull of a very massive object at the center, because only something with enormous mass can force gas to move at such extreme velocities while still keeping it in orbit around the core region. By measuring how wide these spectral lines are, scientists can estimate how fast the gas is moving, and from that, they can work backward to estimate the mass of the object holding it in orbit. And this method led to the conclusion that TON 618 contains a black hole with a mass of around 66 billion times the mass of the Sun, placing it at the upper end of known black hole sizes and possibly among the most massive ever confirmed through direct observational methods. But the measurement does not stop there, because once mass is estimated, scientists can also calculate the size of the event horizon, which is the boundary where the escape velocity becomes equal to the speed of light, and anything that crosses this boundary cannot return, not even light itself. And for TON 618, this boundary is so large that it stretches far beyond the scale of our entire solar system, making it one of the most extreme known gravitational regions in the universe. What makes this even more striking is that this event horizon is not a solid surface. It is not a physical wall or object you could touch. Instead, it is a boundary in space defined purely by gravity, meaning it marks the point where the structure of space itself becomes so curved that all paths lead inward. And for TON 618, this region of space is enormous, meaning the black hole does not act like a small central point, but like a massive zone where normal physics behaves in extreme ways over a large volume. The structure surrounding TON 618 continues to play a key role in how it is studied, because the quasar is powered by an accretion disk, which is a rotating system of gas and dust that is slowly falling into the black hole. And this disk is not calm or stable. It is extremely hot and highly energetic, with material moving at speeds close to a significant fraction of the speed of light. And as this material collides and compresses, it produces intense radiation across multiple wavelengths, including ultraviolet, visible light, and X-rays. This accretion disk is what makes TON 618 visible across billions of light years, because the black hole itself does not emit light. But the matter around it becomes so hot and energetic that it shines brighter than entire galaxies, and in many cases, the brightness of the quasar can completely overpower the light from its host galaxy, making it difficult for astronomers to observe the galaxy structure directly without filtering out the central glow. Another important feature connected to TON 618 is the way energy is released from the system, because not all matter falling into the black hole goes straight across the event horizon. Instead, some of it is redirected and accelerated outward through powerful magnetic fields, creating high-speed jets that can extend far beyond the central region. And although the full jet structure of TON 618 is not as directly mapped as some radio galaxies, the same physical process is believed to be active in its core, contributing to energy output on a massive scale. The scientific importance of TON 618 goes beyond just its size, because it also creates a major challenge for understanding how black holes grow in the early universe, since this object is observed at a time when the universe was much younger, meaning its light has taken billions of years to reach us. And this implies that such an enormous black hole already existed relatively early in cosmic history, which raises a major question about how it reached such a large mass in such a short time compared to the age of the universe at that point. Black holes are thought to grow through a combination of feeding on surrounding gas, merging with other black holes, and slowly increasing mass over time, but reaching tens of billions of solar masses requires either extremely efficient feeding over long periods or very unusual early conditions where massive seed black holes formed quickly after the first stars and galaxies appeared. And TON 618 sites right at the center of this problem because its size pushes the limits of standard growth models. This is often referred to as the early universe black hole formation problem, where observations like TON 618 do not fully match simple growth timelines, because if black holes started from small stellar remnants, it would take a very long time to reach this scale. But TON 618 appears to have reached this level while the universe was still relatively young, which suggests that either growth was much faster in the early universe, or that some black holes started from much larger initial seeds than previously thought. At the same time, TON 618 also helps scientists test the upper limits of black hole growth in general, because there is a point where feeding becomes unstable due to radiation pressure, meaning the energy released by infalling matter can push outwards strongly enough to limit how much material the black hole can consume at once, creating a kind of natural balance known as an accretion limit. And studying TON 618 helps researchers understand how black holes behave when they approach these extreme conditions. Hercules Corona Borealis Great Wall. The Hercules Corona Borealis Great Wall is not a normal kind of space object that you can point a telescope at and see directly, because there is no clear image of it, like a galaxy or a star cluster. Instead, it is something that was discovered through patterns hidden inside very powerful explosions called gamma-ray bursts. And this already makes it different from most things in astronomy, because it was not found by looking at light in a simple way, but by studying how rare short bursts of extreme energy are spread across the sky over very long distances. Gamma-ray bursts, often shortened to GRBs, are some of the most powerful explosions in the universe, and they happen when massive stars collapse or when neutron stars collide, releasing huge amounts of energy in a very short time. And these bursts are so bright that they can be detected across billions of light years, even from the early universe, which makes them useful as markers for studying very distant regions of space, because each burst is like a signal coming from a specific place in the deep universe. And when enough of these signals are collected, scientists can start to map how they are distributed across the sky. In 2013, astronomers studying gamma-ray burst data began to notice something unusual, because instead of being evenly spread across the sky, the bursts seemed to cluster in one very large region, and this clustering was not small or local. It was spread across a huge portion of the sky in a way that did not match expectations from standard cosmological models, which assume that on very large scales, the universe should look mostly uniform, meaning matter should be distributed evenly when viewed over enough distance. At first, this kind of pattern is not immediately taken as proof of a real structure, because in astronomy, data can sometimes show uneven patterns just by chance, especially when dealing with limited samples. So scientists carefully tested whether the clustering was real or just a random effect. And they compared it with models that simulate how gamma-ray bursts should be distributed if the universe is uniform, and what they found was that the patterns seemed too strong and too large to be easily explained by random variation alone. As more data was added over time, the same region of clustering continued to appear, and this led to the idea that there might be an extremely large structure in the universe spanning billions of light years, something that could not be seen directly but could be inferred from how these gamma-ray bursts were grouped together in space. And this structure became known as the Hercules Corona Borealis Great Wall. The estimated size of this structure is around 10 billion light-years across, which immediately places it among the largest known features in the observable universe. And to understand how large this is, it helps to remember that the Milky Way galaxy is only about 100,000 light-years wide, meaning this structure would span a distance tens of thousands of times larger than a single galaxy. And even compared to galaxy clusters and superclusters, it still extends far beyond normal cosmic structures that are usually thought to define large-scale organization in the universe. But this measurement is not based on direct imaging, because no telescope has ever captured a picture of the Great Wall itself. Instead, the size is estimated from the distribution of gamma-ray bursts that appear to be associated with it, meaning scientists look at where these bursts occur in space, how far away they are based on redshift measurements, and how they cluster together across the sky. And from this statistical pattern, they infer the possible size of the underlying structure that could be causing this grouping effect. The idea is not that the gamma-ray bursts themselves form the structure, but that they act like markers inside a much larger arrangement of matter. So if many bursts appear in one region of space at similar distances, it suggests that the galaxies producing them may be part of a larger connected system, even if that system is too faint or too spread out to see directly with current telescopes. Unlike galaxies, clusters, or even superclusters that can be mapped through direct observation of light, the Hercules Corona Borealis Great Wall is not visible in a traditional sense, because it does not appear as a single glowing object or a connected shape in images. Instead, it is defined entirely through statistical patterns in high-energy events, meaning its existence depends on analyzing large amounts of data and identifying non-random distributions across space. This makes it very different from most known cosmic structures, because instead of being something that can be photographed or directly traced in optical surveys, it exists as a pattern that emerges only when you study how certain events are spread across the universe. And this means the structure is not defined by edges or boundaries in the usual sense, but by regions where the density of gamma-ray bursts is higher than expected. Scientists think that if this structure is real, it would contain large numbers of galaxies and galaxy clusters arranged in a connected pattern that stretches across billions of light years. But because the galaxies themselves are extremely faint at such distances, and because light from those regions takes billions of years to reach us, it is very difficult to directly map the full structure using normal imaging methods, which is why gamma-ray bursts are used as indirect indicators. Detection method: statistical mapping of gamma-ray bursts. The detection process for the Hercules Corona Borealis Great Wall is based on statistical analysis, which means scientists do not look for a single image or object, but instead analyze large datasets of gamma-ray burst locations and compare them against what would be expected if the universe were evenly distributed on large scales. In a uniform universe, gamma-ray bursts should appear roughly evenly spread when enough of them are observed, especially when looking at very large volumes of space. But when researchers plotted the positions of known bursts, they found that a significant number of them were concentrated in one region, spanning a very large area of the sky. And this concentration did not match what would normally be expected from random distribution models. To test this, scientists used simulations that model how gamma-ray bursts should appear if galaxies are distributed randomly on large scales, and then compared those simulations with real observational data. And the real data showed a stronger clustering effect than most random models predicted, which suggested that there might be an underlying large-scale structure influencing where these bursts occur. However, this type of detection is not simple or final, because statistical methods depend heavily on sample size, selection bias, and observational limits, meaning that if the dataset is incomplete or uneven, it can sometimes create patterns that look significant even when they are not fully representative of the entire universe. And this is one of the main reasons why the existence of the Hercules Corona Borealis Great Wall is still debated. One of the most important ideas in cosmology is the cosmological principle, which states that on very large scales, the universe should look roughly the same in all directions, meaning matter should be evenly distributed when viewed over enough distance, and no single region should be dramatically different in size or structure compared to others. But the possible existence of the Hercules Corona Borealis Great Wall directly raises questions about this assumption, because a structure that spans around 10 billion light-years would be extremely large compared to expected limits of uniformity. If such a structure truly exists, It would suggest that matter in the universe can be organized into patterns much larger than current models predict, which would require adjustments to how scientists understand large-scale structure formation, galaxy distribution, and the early growth of cosmic networks. Because standard models based on dark matter and expansion predict that structures should become more uniform beyond certain scales, not more connected in massive continuous regions. However, not all scientists agree that the Great Wall is a real physical structure, because some researchers argue that the observed clustering could be the result of statistical bias, meaning that the way gamma-ray bursts are detected and recorded might naturally produce uneven patterns, especially since GRBs are rare events, and the sample size is still relatively limited compared to the vast size of the universe. And when working with small datasets in very large volumes, random clustering can sometimes appear stronger than it actually is. Another point of debate is observational coverage, because gamma-ray burst detection depends on instruments that do not observe the entire sky evenly at all times, meaning some regions of space are monitored more frequently than others, and this uneven coverage can influence how bursts appear to be distributed, creating artificial patterns that may not reflect the true underlying structure of the universe. Despite this uncertainty, the Hercules Corona Borealis Great Wall remains one of the most interesting large-scale patterns ever identified in cosmology. Because even if it turns out to be partially or fully a statistical effect, it still highlights how little is known about the distribution of matter at the largest scales. And it shows how difficult it is to map the universe when dealing with events that are rare, extremely distant, and spread across billions of years of cosmic history. As more gamma-ray bursts are detected, and as future space observatories collect larger and more complete data sets, scientists will be able to test this structure with better accuracy, comparing new data against older maps, and refining their models of how galaxies and high-energy events are distributed across space, and whether the Hercules Corona Borealis Great Wall is a true cosmic structure or a pattern created by limited observations remains one of the key open questions in understanding the largest possible scales of the universe. Laniakea supercluster, our cosmic home. Laniakea supercluster was not discovered in the usual way, where a telescope points at the sky and finds a new glowing object, because nothing about it appears as a single, visible shape that you can isolate in an image. Instead, it was discovered through motion, through the way galaxies move through space, and this already makes it very different from most cosmic structures that were known before it, because instead of being defined by light or brightness, it is defined by flow, by gravity, and by the hidden movement of thousands of galaxies being pulled in different directions across the universe. The discovery happened in 2014 when astronomers used a method called galaxy velocity field mapping, which is a way of studying not just where galaxies are, but how they are moving, because every galaxy in space is not standing still. It is moving due to the expansion of the universe and also due to gravitational pulls from other nearby structures. And by separating these two types of motion, scientists can map out how matter is flowing across very large regions of space. This is where the idea of peculiar velocity becomes important, because galaxies have two kinds of motion at the same time. One is the motion caused by the expansion of the universe, where space itself is stretching and pushing galaxies apart, and the other is the motion caused by gravity, where galaxies are pulled toward massive regions of matter. And this second type of motion is what scientists call peculiar velocity, meaning the movement that is not explained by expansion alone. By carefully measuring these velocities for thousands of galaxies, astronomers were able to map the direction of motion for each galaxy, and then connect those motions into a large-scale flow pattern. And what they found was not random movement, but a clear structure where many galaxies were all moving toward a common region, as if they were flowing along invisible paths shaped by gravity. And when this entire flow field was reconstructed, it revealed a massive connected region that had not been clearly defined before. This structure was named Laniakea, which means immense heaven in Hawaiian, and it was defined not as a simple cluster or a group of galaxies, but as a supercluster region where galaxies are gravitationally linked through motion, meaning that everything inside it is part of a shared flow toward a central gravitational area known as the Great Attractor, which acts like a massive anchor point, pulling galaxies inward across hundreds of millions of light years. What makes this discovery important is that it changed the way scientists define where the Milky Way actually belongs in the universe, because before Laniakea was mapped, the Milky Way was often placed within the Virgo supercluster, which was thought to be a large grouping of galaxies, including our local cluster. But after studying galaxy motion in more detail, scientists realized that the Virgo supercluster is actually just a small part of a much larger flow system, and that the Milky Way is not just part of a local cluster, but part of a far larger structure stretching across a much wider region of space. Laniakea spans about 520 million light-years across, which makes it one of the largest known structures connected by gravitational flow in the local universe. And this distance is not measured by simply looking at how far galaxies appear in the sky, but by tracking how their velocities change depending on their position relative to the Great Attractor. And by mapping these motions in 3 dimensions, scientists can outline the boundary where galaxies are influenced by Laniakea's gravitational field. Inside this region, there are more than 100,000 galaxies, including the Milky Way, all moving through space under the influence of combined gravitational forces. And instead of being evenly scattered or isolated, these galaxies are organized into filaments, groups, and clusters that all connect through the same large-scale flow pattern, meaning that even though they look separate in the sky, they are actually part of a single, connected dynamic system when viewed in terms of motion. The size of 520 million light-years is important because it represents the scale at which gravitational influence from Laniakea dominates over the expansion of the universe in this region, meaning that within this boundary, galaxies are not just drifting apart due to cosmic expansion, but are being guided by gravity toward a central region, creating a structure that is defined more by movement than by static position. Laniakea is not a solid object or a simple cluster with clear edges. Instead, it is a network of galaxies moving along gravitational flow lines, and at the center of this flow is the Great Attractor, a region of extremely strong gravitational pull that influences the motion of galaxies across vast distances, even though it is not fully visible in optical light due to dust and other structures blocking direct observation in certain directions. Galaxies within Laniakea do not orbit the center in simple circular paths like planets around a star. Instead, they move along curved trajectories shaped by the combined gravity of many mass concentrations, including galaxy clusters, dark matter regions, and large-scale filaments, and these paths gradually guide them toward the central region over extremely long timescales, meaning that the structure is constantly evolving as galaxies continue to move through it. The filaments inside Laniakea act like cosmic highways, guiding galaxies through space along paths of least resistance, and these filaments are not physical structures in the traditional sense, but regions where matter density is slightly higher than surrounding space, creating gravitational channels that influence how galaxies move, and over time, these channels help shape the overall structure of the supercluster. One of the key features of Laniakea is that its boundaries are not fixed in a rigid way, because unlike solid objects, its edge is defined by where galaxy motion changes direction, meaning that if a galaxy is moving toward the Great Attractor, it is considered part of Laniakea. But if it is moving away or toward a different gravitational center, it belongs to another structure, and this makes the boundary a dynamic surface shaped by motion rather than a fixed line in space. The method used to discover Laniakea relies on a detailed study of galaxy motion, where scientists measure both the redshift of galaxies and their peculiar velocities. And by comparing these two types of data, they can separate the effects of cosmic expansion from local gravitational influence, allowing them to see how galaxies are actually moving relative to each other in space. Redshift alone tells us how fast a galaxy is moving away due to the expansion of the universe, but it does not tell the full story, because galaxies also have their own motion caused by gravity. And this is why redshift data must be combined with distance measurements and velocity corrections to build a full picture of movement. And once this is done for a large number of galaxies, a flow map of the universe begins to appear. In the case of Laniakea, this flow map revealed that galaxies are not randomly distributed in motion, but instead follow a structured pattern where many of them are moving in the same general direction toward a central gravitational region. And when these motion lines are traced backward, they outline a large connected volume of space that defines the supercluster. This approach is different from earlier methods that defined superclusters based mainly on galaxy positions, because position alone can be misleading at large scales, especially when dealing with an expanding universe where distances are constantly changing. But motion-based mapping provides a clearer picture of how matter is actually organized dynamically, revealing connections that were not visible through position data alone. Laniakea changed the way scientists describe the cosmic address of the Milky Way, because instead of simply saying that we are part of the Virgo supercluster, it now becomes clear that the Milky Way is part of a much larger system defined by gravitational flow, meaning our galaxy is not just sitting in a local group, but is being carried along a massive stream of motion that extends across hundreds of millions of light years. This also changed how superclusters are understood, because before Laniakea, superclusters were often thought of as large but relatively stable structures, where galaxies were loosely bound together by gravity. But the discovery of Laniakea showed that many of these structures are not permanently bound in a stable way. Instead, they are dynamic flow systems, where galaxies are constantly moving, entering, and leaving different regions over time. This means that superclusters are not fixed objects in the long term, because the expansion of the universe continues to stretch space, and while gravity can dominate in certain regions, it does not always hold entire superclusters together forever. So over very long timescales, these structures can change shape, lose connections, or merge into other flow systems, depending on how gravity and expansion interact across large distances. Laniakea also shows that the universe is not just a collection of isolated clusters and galaxies, but a connected system where motion, gravity, and large-scale structure are deeply linked. And by studying these connections, scientists can better understand how matter is distributed on the larger scales, how galaxies move through space over time, and how the cosmic web is shaped by both visible matter and dark matter that cannot be seen directly, but reveals itself through its gravitational effects. Shapley supercluster. The first hints of the Shapley supercluster go back to the 1930s, when astronomers began noticing that one region of space contained an unusually high number of bright galaxy clusters compared to surrounding areas. And at the time, this was not fully understood, because the tools available were still limited, and the idea of large-scale cosmic structure was still developing. In those early decades of astronomy, scientists could see galaxies and clusters, but they did not yet have a full map of how those clusters were connected across very large distances. So when Edwin Hubble and other early observers catalogued galaxies, they treated clusters as separate systems rather than parts of a larger connected structure. But as more data was collected, especially from southern sky surveys, one region began to stand out due to its density and brightness. And that region would later be recognized as the Shapley supercluster. The name comes from Harlow Shapley, an astronomer who studied the distribution of globular clusters and helped shift the understanding of the Milky Way's position in the universe. And although he did not directly map the supercluster in its modern form, his work contributed to the early recognition that galaxy distributions are not random, but instead show strong patterns and concentrations. And over time, as more precise surveys were carried out, especially in the late 20th century and early 21st century, the structure became clearer and more defined. Modern observations using large-scale redshift surveys confirmed that the region identified by early astronomers was not just a simple cluster of galaxies, but part of a much larger system made up of many galaxy clusters connected over a vast region of space. And with improved technology, including digital sky surveys and better distance measurements, scientists were able to refine its boundaries and understand that it is one of the most massive nearby superclusters in the observable universe. Unlike a single galaxy or even a single galaxy cluster, the Shapley supercluster is not defined by one central object. Instead, it is a region where many massive clusters are grouped together in a dense concentration, and this density is what makes it stand out compared to surrounding cosmic regions, because while space on large scales is filled with filaments and voids, the Shapley region contains an unusually high number of rich clusters packed relatively close together on cosmic scales. The Shapley supercluster spans a region of space that stretches across hundreds of millions of light years, making it one of the largest and most massive structures in the nearby universe, and unlike smaller galaxy groups where only a few galaxies are bound together, this supercluster contains a large number of full galaxy clusters, each cluster containing hundreds or even thousands of galaxies, meaning that the total number of galaxies within the Shapley region reaches into the tens of thousands when all connected clusters are counted together. What makes its size especially important is not just the physical width of the region, but the concentration of mass within it, because mass in astronomy is not just visible matter like stars and gas, but also dark matter, which cannot be seen directly, but is detected through its gravitational effects. And in the Shapley supercluster, the total mass is extremely high, making it one of the strongest gravitational regions in the nearby universe. The structure is not a single uniform shape. Instead, it is spread out across multiple connected clusters, forming a kind of thickened region within the cosmic web, where filaments of galaxies converge and overlap, creating dense nodes of matter. And these nodes are what form the individual galaxy clusters that make up the supercluster, meaning it is more like a large interconnected network than a single object with clear boundaries. Because of its size and mass, the Shapley supercluster plays a major role in shaping the motion of galaxies in its surrounding region, including galaxies that are not directly inside it, but are still affected by its gravitational pull. And this influence can extend over very large distances, meaning that even galaxies far away from the center of the supercluster can show signs of being pulled toward it. The Shapley supercluster is best understood as a dense region where many galaxy clusters are packed together within the cosmic web. And these clusters are not isolated because they are connected through filaments of galaxies and dark matter that stretch between them, forming a complex network of matter that spans a huge region of space. Inside this structure, there are multiple rich galaxy clusters, each one containing large numbers of galaxies held together by gravity. And these clusters themselves are part of larger groupings, meaning that the structure has multiple layers, starting from individual galaxies, then groups of galaxies, then clusters, and finally the full supercluster region that connects all of these components together. The distribution of matter in the Shapley region is not uniform, because some areas are extremely dense with clusters, while other areas are more spread out, and this uneven distribution is what creates the overall structure, with dense cores connected by thinner filaments, forming a web-like pattern that reflects the underlying distribution of dark matter, that shapes how visible matter moves and gathers over time. Unlike some superclusters that are loosely connected and may eventually separate due to cosmic expansion, the Shapley supercluster is dense enough that its internal gravitational influence is very strong, meaning many of its components are significantly affected by each other's gravity. And this makes it one of the most dynamically important structures in the local universe. One of the most important features of the Shapley supercluster is its strong gravitational influence on nearby galaxies, including galaxies that are not directly inside it, because mass on this scale does not just affect local regions, it affects motion across vast distances. And this influence can be detected by studying how galaxies move, compared to what would be expected from cosmic expansion alone. In many cases, galaxies in surrounding regions show motion patterns that cannot be fully explained by uniform expansion, meaning they appear to be drifting towards certain directions more than others. And one of the major contributors to this motion is the Shapley supercluster, which acts as a strong gravitational center, pulling surrounding matter toward its region. This effect is part of what scientists study when they analyze large-scale cosmic flow, because galaxies are not only moving outward due to the expansion of the universe, they are also being pulled by massive structures like Shapley. And this combination of expansion and gravity creates complex motion patterns that can only be understood by mapping both position and velocity across large volumes of space. The influence of Shapley is also connected to what is known as bulk flow, which is the overall movement of groups of galaxies in a shared direction. And observations have shown that a significant portion of local galaxy motion appears to be influenced by massive structures in the direction of the Shapley region, suggesting that its gravitational reach extends far beyond its visible boundaries. This makes it an important reference point for understanding how matter is distributed in the local universe, because it helps explain why galaxies do not move randomly, but instead show coordinated motion patterns that reflect the presence of large unseen or partially visible mass concentrations spread across the cosmic web. The Shapley supercluster plays a key role in explaining cosmic flow anomalies, which are cases where galaxy motion does not fully match predictions based on uniform expansion models. And these anomalies appear when galaxies in large regions seem to be moving in preferred directions that cannot be explained by local structures alone. By studying the Shapley region, scientists are able to test how much of this motion can be explained by known mass concentrations and how much might be influenced by even larger or more distant structures, and this helps refine models of how gravity operates on the largest scales, especially when combined with the effects of dark matter and dark energy. It also helps improve understanding of how superclusters form and evolve over time, because the presence of such a massive and dense structure suggests that galaxy clusters can merge and align along filaments in ways that create long-lasting regions of high density, even while the universe continues to expand. And this balance between gravity and expansion is one of the key areas of study in modern cosmology. The Shapley supercluster also serves as a major reference point for mapping the nearby universe, because its strong mass concentration affects how scientists interpret the motion of galaxies in surrounding regions, meaning that any accurate model of local cosmic structure must include its gravitational influence in order to correctly describe observed galaxy velocities. The Sloan Great Wall. The Sloan Great Wall is one of those discoveries that changed how scientists think about the universe on its biggest scales, because before it was mapped, many models of cosmology assumed that once you zoom out far enough, the universe should start to look more and more even, with galaxies spreading out in a fairly uniform way. But when the Sloan Digital Sky Survey began producing large, detailed maps of galaxies, something appeared that did not fit that simple expectation, and that something was a massive connected structure of galaxies stretching across a distance so large that it forced scientists to rethink how matter is arranged on the larger scales we can observe. The discovery came in 2003 through data collected by the Sloan Digital Sky Survey, often shortened to SDSS, which is one of the most important astronomical mapping projects ever created, designed to scan large portions of the sky and record the position and distance of millions of galaxies, not just in 2 dimensions like older sky maps, but in 3 dimensions, which means not only where a galaxy appears in the sky, but also how far away it is based on how its light has shifted due to the expansion of the universe. Before projects like SDSS, galaxy surveys were limited in scope, meaning they could only map relatively small sections of the sky or only a limited number of galaxies at a time. But SDSS changed this by using automated telescopes and advanced imaging systems that could capture huge amounts of data night after night, building up a detailed 3D map of the universe piece by piece. And as this map grew, scientists began to see that galaxies were not scattered randomly, but arranged in patterns that looked like filaments, clusters, and walls, forming what is now known as the cosmic web. The Sloan Great Wall emerged from this data as one of the most striking structures in the survey, because it was not just a small cluster or a local grouping of galaxies, but a massive connected region where galaxies and galaxy clusters appeared to line up along a long, continuous structure, stretching across a huge part of the mapped sky. And when its full scale was calculated, it reached about 1.4 billion light-years in length, making it one of the largest known structures in the observable universe at the time of its discovery. To understand what this size means, it helps to compare it with something more familiar, like a single galaxy. For example, the Milky Way is about 100,000 light-years across, which already feels enormous when compared to distances within our solar system. But the Sloan Great Wall is so large that you could place thousands upon thousands of Milky Way galaxies end to end along its length, and still only cover a small fraction of its full extent, which shows how far beyond normal galactic scales this structure actually is. The discovery of the Sloan Great Wall did not come from seeing a single object that looked like a wall, because there is no visible wall in space in the traditional sense. Instead, it came from analysing the distribution of galaxies in redshift space, which means plotting galaxies based on how their light has shifted toward redder wavelengths due to the expansion of the universe, and using this redshift information to estimate how far away each galaxy is, allowing scientists to build a three-dimensional map of where galaxies are located in space. When this 3D map was constructed from SDSS data, galaxies did not appear evenly spread. Instead, they formed clusters connected by long threads of matter, and in one region, these threads became especially dense and extended over a very large distance, forming a connected structure that stood out clearly compared to surrounding regions, and this is what became known as the Sloan Great Wall. This structure is best described as a filament of galaxy clusters, meaning it is not a solid object like a wall in the everyday sense, but a long, thick region of space where galaxies are more densely packed than in surrounding areas. And within this filament, there are multiple galaxy clusters, each cluster containing hundreds or thousands of galaxies bound together by gravity. And these clusters are linked by regions of slightly lower density that still contain enough matter to form a continuous connection across vast distances. The idea of a filament is important in modern cosmology because it reflects how matter is distributed in the universe on large scales, where galaxies are not randomly scattered, but instead follow patterns shaped by gravity and the underlying distribution of dark matter, which acts like a hidden structure guiding where visible matter collects. And over billions of years, small fluctuations in density grow under gravity, forming the large-scale network of filaments and voids that make up the cosmic web. The Sloan Great Wall sits as one of the most prominent examples of this cosmic web structure, because it shows how filaments can grow to extreme sizes when conditions allow matter to accumulate along extended regions of space. And it demonstrates that galaxy clusters are not isolated systems, but part of larger connected formations that stretch far beyond individual cluster boundaries. The method used to detect this structure is based on redshift mapping of galaxies, which means measuring how much the light from each galaxy has shifted toward the red end of the spectrum. And this shift happens because the universe is expanding. So galaxies that are farther away appear more redshifted, and by combining redshift data with angular position in the sky, scientists can reconstruct a full three-dimensional map of galaxy positions across huge volumes of space. In the Sloan Digital Sky Survey, this method was applied to millions of galaxies, and the result was one of the most detailed maps of the universe ever created at that time, allowing scientists to see not just isolated clusters, but the full structure of how galaxies connect across space. And within this map, the Sloan Great Wall stood out as a continuous, high-density region that extended across a much larger scale than most known structures. What made this discovery especially important is that it provided one of the first clear pieces of evidence for extremely large-scale structure in the universe, meaning it showed that matter is organized into connected formations that can span over 1 billion light-years. And this was a major step forward in confirming the idea of the cosmic web, which predicts that galaxies and clusters are linked in a vast network of filaments and voids shaped by gravity and dark matter. Before this kind of detailed mapping existed, it was difficult to prove that such large structures existed, because earlier surveys did not cover enough of the sky or enough galaxies to reveal full three-dimensional patterns. But with SDSS data, scientists could finally see enough of the universe at once to identify large-scale structures with confidence, and the Sloan Great Wall became one of the strongest examples of this new understanding. The importance of this structure is not only in its size, but also in what it tells us about how the universe formed over time. Because according to cosmological models, The early universe was almost uniform, with only small fluctuations in density. And over billions of years, gravity caused these small differences to grow, forming galaxies, clusters, and eventually large-scale structures like filaments and walls. And the Sloan Great Wall represents one of the most developed examples of this process in the nearby universe. It also shows how matter is not evenly distributed even on extremely large scales, because even when you look across hundreds of millions or billions of light years, the universe still contains regions where matter is concentrated into long structures and other regions where matter is sparse, forming large empty voids between filaments. And the Sloan Great Wall exists as part of this contrast, sitting in a dense region of the cosmic web, while other nearby areas remain relatively empty. Another important aspect of the Sloan Great Wall is that it helps scientists test models of large-scale structure formation, because computer simulations of the universe based on dark matter and cosmic expansion predict that structures like filaments and walls should form naturally over time. But observing real structures like this provides direct evidence that these models are correct on large scales, while also helping refine details about how fast and how far these structures can grow. The Sloan Great Wall also raised new questions about the limits of structure size in the universe, because while it is extremely large, it still exists within the observable universe, and its presence suggests that matter can organize into connected formations over distances much larger than previously confirmed, which led scientists to continue searching for even larger structures, some of which have been proposed in later studies. At the same time, the structure is not static, because galaxies within it are not fixed in place. Instead, they are moving under the influence of gravity and cosmic expansion, meaning that over very long timescales, the shape of the Sloan Great Wall will change as galaxies move, clusters interact, and the large-scale structure of the universe continues to evolve, even though on human timescales it appears stable. Even though it is called a wall, it is not a barrier or a solid object, but a statistical and gravitational pattern formed by the distribution of galaxies, and its existence is only known through careful measurement of many individual galaxies and how they are arranged in space. Meaning that without large surveys like SDSS, structures like this would remain hidden in the background of the universe, undetectable at smaller scales of observation. Huge LQG, Large Quasar Group. The huge LQG, which stands for Large Quasar Group, is one of the most unusual structures ever identified in the universe, not because it is a single object that can be seen directly, but because it appears as a massive pattern formed by some of the brightest and most distant objects in space. And these objects are quasars, which are extremely powerful active galactic cores powered by supermassive black holes. And when scientists first noticed this grouping in 2013, it did not look like something that should exist under normal assumptions about how matter is spread across the universe at very large scales. The discovery came from quasar clustering analysis, which is a method where astronomers take large catalogues of quasars collected from surveys like the Sloan Digital Sky Survey and study how they are distributed across the sky in both position and distance, because quasars are useful for this kind of work due to their extreme brightness, which allows them to be seen across billions of light years, meaning they act as markers for very distant regions of the universe, even from times when the universe was much younger than it is today. Before this analysis, quasars were already known to be scattered across the universe, often appearing randomly distributed when viewed on very large scales, which matched expectations from cosmological models that suggest the universe should become more uniform as you zoom out far enough. But when scientists started analysing a large sample of quasars together, they began to notice that in one region of the sky, quasars were not just randomly placed, but appeared to form a connected structure spanning an extremely large distance. At first, this was not immediately interpreted as a real structure, because in astronomy, patterns can sometimes appear due to incomplete data or observational bias, especially when dealing with very rare objects like quasars. But as more data was added and more quasars were mapped, the pattern remained consistent, showing a group of quasars that were unusually close together in space compared to what standard random distribution models would predict. This grouping was eventually named the huge LQG, and what made it stand out immediately was its scale, because when its full extent was measured, it appeared to stretch across about 4 billion light-years, which places it among the largest known structures in the observable universe. And to understand this scale in simple terms, it means that light travelling from one end of this structure to the other would take 4 billion years, which is a significant fraction of the age of the universe itself. The huge LQG is not a solid structure in the traditional sense. It is not a single object with clear edges or a defined boundary. Instead, it is a group of quasars that appear to be linked in space, forming a large alignment that suggests they are part of a shared large-scale structure, and this alignment is what makes it stand out from random distributions, because instead of being scattered evenly, the quasars appear to follow a connected pattern across a vast region of space. Quasars themselves are not small or simple objects. Each one is powered by a supermassive black hole at the center of a galaxy. And as matter falls into these black holes, it forms a highly energetic accretion disk that produces enormous amounts of light and radiation, often making quasars brighter than the entire galaxy that surrounds them. And this extreme brightness is what allows them to be detected across billions of light-years, making them valuable tools for mapping the distant universe. In the case of the huge LQG, the quasars involved are not physically connected in the sense of being close neighbours like stars in a galaxy. Instead, they are separated by enormous distances, but they appear to form a large-scale alignment that suggests they are part of a broader structure in the cosmic web, where matter is not randomly scattered, but arranged into filaments and nodes shaped by gravity and dark matter over billions of years. The measurement of the huge LQG size, around 4 billion light-years across, comes from analysing the positions of these quasars in three-dimensional space, which requires combining their angular positions in the sky with distance estimates based on redshift, and redshift is a measure of how much the light from distant objects has been stretched due to the expansion of the universe, allowing scientists to estimate how far away each quasar is and place it in a 3D map of the cosmos. Once this 3D map is constructed, scientists can look for clustering patterns by checking how close objects are to each other in space, compared to what would be expected if they were randomly distributed. And in the case of the huge LQG, the clustering is strong enough that it forms a connected structure extending across billions of light-years, which is far larger than most previously known galaxy groups or quasar associations. What makes this structure particularly interesting is that it is not made of galaxies themselves, but of quasars, which are relatively rare compared to normal galaxies, and this rarity makes any large grouping statistically more significant. Because when rare objects cluster together over such large distances, it becomes less likely that the pattern is caused by chance alone, and more likely that there is an underlying structure influencing their distribution. The structure itself is not uniform. It is not a straight line or a simple shape. Instead, it appears as a loosely connected network where quasars are distributed along a broad region of space, forming a kind of elongated grouping that suggests the presence of large-scale filaments in the cosmic web. And these filaments are thought to be shaped by the distribution of dark matter, which acts as a hidden framework guiding how visible matter collects over time. One of the most important aspects of the huge LQG is that it pushes the limits of what was previously thought to be the maximum size of coherent structures in the universe, because standard cosmological models suggest that beyond a certain scale, matter should become more evenly distributed, meaning that structures larger than a few 100 million light-years should not remain strongly connected. But the huge LQG appears to extend far beyond this range, raising questions about how such a large alignment can exist. At the same time, it is important to understand that the huge LQG is not necessarily a single gravitationally bound object, meaning the quasars within it are not all pulled together by one shared gravitational force. Instead, they are part of a large-scale pattern that reflects how matter was distributed in the early universe and how those initial conditions evolved over time into the structures we see today, meaning it is more of a statistical and spatial pattern than a tightly bound physical system. Scientific controversy, detection method, and why this structure still divides astronomy. Unlike many cosmic discoveries that clearly fit into existing models, this one immediately raised tension between observation and theory, since a structure stretching across around 4 billion light-years made scientists ask whether something this large could really exist as a single connected feature in the universe, or whether what they were seeing was a pattern created by how the data was collected and interpreted. The main reason for this debate comes from a core idea in cosmology called the cosmological principle, which says that when you look at the universe on very large scales, it should appear roughly uniform, meaning matter should be evenly spread out when you average over enough distance, and while small and medium structures like galaxies, clusters, and even superclusters are expected, there is an assumed upper limit beyond which the universe should smooth out. But the huge LQG appears to extend beyond that expected limit, which is why it became controversial almost immediately after its identification. The structure is described as possibly violating this principle, not because it proves the universe is uneven everywhere, but because it suggests that coherent patterns of matter might exist on scales larger than what standard models predict should remain connected. And this does not mean the universe is broken or incorrectly understood, but it does mean that either the structure is not truly a single connected system, or that current understanding of large-scale cosmic formation needs refinement to explain how such alignments could form. One of the strongest arguments in this debate is that the huge LQG is not a directly observed object, meaning there is no image of a continuous physical structure linking all of the quasars together. Instead, what exists is a statistical grouping based on their positions and distances, and this means the structure is inferred rather than seen, and anything inferred from data must always be tested carefully for bias, selection effects, and random clustering that can appear stronger than it really is when working with rare objects. The detection method behind the huge LQG is based on statistical quasar grouping using data from large surveys like the Sloan Digital Sky Survey, where astronomers collect information about the positions of quasars across the sky and their redshift values, which give estimates of how far away they are, and by combining this information into a three-dimensional map, they can measure distances between quasars and identify whether any of them form clusters that are more tightly grouped than expected. In this process, scientists apply algorithms that search for groups of quasars within a certain maximum separation distance, meaning they define a scale at which quasars are considered part of the same structure if they are close enough in space. And when this method was applied to the SDSS quasar catalogue, the huge LQG appeared as a grouping that exceeded the expected size limit for random clustering, leading to its identification as a potential large-scale structure. However, this method also introduces complexity, because the choice of separation distance, the density of the dataset, and the way sampling is done can all affect whether a group appears significant or not. And when working with very large distances and relatively rare objects like quasars, even small changes in assumptions can lead to large changes in the resulting structure maps, which is one of the main reasons why the huge LQG is still debated. Another important factor in the controversy is sample size, because although SDSS contains a large number of quasars, in cosmic terms they are still sparse compared to galaxies. And when you try to map structures across billions of light-years using sparse data points, there is always a risk that random alignments can appear more meaningful than they actually are, especially when viewed in projection across the sky. Some researchers argue that the huge LQG could be a result of statistical bias, meaning that the distribution of observed quasars might naturally produce apparent clustering simply due to how surveys cover the sky, how sensitive instruments are in different regions, and how selection criteria filter which quasars are included in the final dataset. And when these factors are not perfectly uniform, they can create artificial patterns that look like large structures but do not necessarily reflect true physical connections. On the other hand, supporters of the structure argue that even if the grouping is influenced by observational limits, the scale and consistency of the alignment across different analyses suggest that there may still be an underlying real feature in the distribution of matter, possibly tracing a large filament or region of enhanced density in the cosmic web, where quasars tend to form more frequently due to higher rates of galaxy interaction and black hole activity. This leads to an important point about what the huge LQG actually represents, because it is not a single gravitationally bound object like a galaxy cluster, meaning the quasars within it are not all held together by one shared gravitational system. Instead, they are spread across such large distances that they are likely influenced by different local environments, and the grouping is more about large-scale spatial correlation than direct physical connection. In other words, the huge LQG is not a structure where everything is tightly linked like stars in a galaxy, but rather a pattern where active galactic nuclei appear more frequently in a certain region of space, suggesting that this region may have had conditions in the early universe that favoured the formation or visibility of quasars, such as higher matter density or more frequent galaxy interactions. The detection of this kind of pattern is especially important because quasars are used as probes of the distant universe, and when they appear clustered on such large scales, they provide clues about how matter was distributed in the early stages of cosmic evolution, meaning that even if the exact boundaries of the huge LQG are uncertain, the pattern itself still carries information about large-scale structure formation. Another key issue in the scientific debate is the concept of scale in cosmology, because one of the goals of large-scale surveys is to determine the scale at which the universe becomes statistically uniform, meaning that beyond a certain distance, the distribution of matter should look smooth when averaged over large volumes. But structures like the huge LQG challenge this by appearing to extend beyond those expected scales, raising questions about whether the transition to uniformity happens at larger distances than previously thought, or whether current datasets are not sufficient to confirm that transition clearly. This does not necessarily mean that cosmological models are wrong, but it does highlight the limits of current observational data, because even with powerful surveys like SDSS, we are still sampling only a fraction of the observable universe, and our ability to detect very large structures depends heavily on how complete and uniform that sampling is across different regions of the sky. Booty's void, one of the largest cosmic voids. When most people imagine the largest things in the universe, they usually think about giant galaxies, enormous black holes, or massive structures made of countless stars spread across impossible distances. The assumption is simple. Bigger means more matter. Bigger means more galaxies. Bigger means more stuff packed into space. But one of the largest structures ever discovered in the universe is famous for the exact opposite reason. It is famous because almost nothing is there. That sounds strange at first, because how can nothing be one of the biggest things ever found? Yet that is exactly what makes the Booty's void so fascinating. It is not known for what it contains. It is known for what it does not contain. Imagine spending decades studying the universe and becoming used to seeing galaxies everywhere. Every direction you point a telescope, there are galaxies. Some are small, some are large, some exist alone. Others gather into groups and clusters. The universe seems crowded. Even in places that look empty, deeper observations usually reveal more galaxies hiding farther away. Now imagine finding a region of space so empty that astronomers initially wondered if something had gone wrong with their observations. That is the story of the Booty's void. Discovered in 1981 during galaxy surveys, the Booty's void immediately stood out because it appeared to contain far fewer galaxies than expected. Scientists were not looking for a giant empty region when they found it. They were simply mapping galaxies and trying to understand how matter is distributed throughout the cosmos. The expectation was that galaxies would show patterns and clustering, but nobody expected to find an enormous region that seemed almost deserted. The discovery happened as astronomers examined the distribution of galaxies in a section of the sky located in the direction of the constellation Bootes. As galaxy positions were plotted and distances were measured, a surprising gap began to appear. Instead of finding galaxies spread throughout the region, researchers found a huge volume of space where galaxies were incredibly scarce. The more they studied the area, the stranger it became. At first, Scientists always have to ask the same question when something unusual appears in data. Is it real? This may sound obvious, but astronomy is filled with examples where strange discoveries later turned out to be errors in observations, problems with equipment, or misunderstandings of data. A single observation is rarely enough to convince researchers, so the region was examined again, and again, and again. Each new observation pointed toward the same conclusion. The emptiness was real. The region, now known as the Bootes Void, appeared to stretch across roughly 330 million light-years. That number is so large that it can become meaningless if you hear it too quickly. So it helps to slow down and think about what it actually means. Light travels at about 300,000 kilometers every second. It moves so fast that it can circle Earth more than 7 times in a single second. Even at that speed, light needs more than 1 second to reach the Moon. It takes over 8 minutes to travel from the Sun to Earth. Yet crossing the Bootes Void would take light around 330 million years. Not thousands of years, not millions of years, hundreds of millions of years. That is the scale of the emptiness astronomers were looking at. To make the size even more surprising, remember that the Milky Way galaxy itself is about 100,000 light-years wide. The Bootes Void is so enormous that you could line up thousands of Milky Ways from one side to the other and still not come close to filling the entire distance. And yet, despite all that space, there are remarkably few galaxies inside. This is what makes the structure so unusual. The universe is not perfectly uniform. Galaxies naturally gather into clusters and filaments. Empty regions are expected to exist between those structures. However, the Bootes Void was much larger and emptier than many astronomers expected when it was first discovered. As researchers studied the region, they realized something important. The universe does not look like a random scatter of galaxies. Instead, it looks more like a giant cosmic network. Galaxies gather together into long filaments stretching across space. These filaments intersect at dense nodes where massive galaxy clusters form. Between these regions lie enormous voids where very little matter exists. When viewed on the larger scales, the universe resembles a gigantic foam. Not foam in the everyday sense, but a similar pattern. Imagine bubbles packed together. The walls between the bubbles contain most of the material. The interiors contain very little. The Bootes Void became one of the clearest examples of one of these cosmic bubbles. This was important because it provided powerful evidence that the large-scale universe is organized into walls and empty regions rather than being evenly filled with galaxies. Before discoveries like this, astronomers knew galaxies clustered together, but mapping giant voids helped reveal the full architecture of the cosmos. The discovery forced scientists to think differently about what emptiness means in astronomy. An empty region in space is never truly empty. Even inside the Bootes Void, there are some galaxies. There is also dark matter, there are particles, there is radiation, there are gravitational fields. Compared to complete emptiness, the void still contains things, but compared to the surrounding universe, it is dramatically underpopulated. If you were somehow able to travel through this region, the view would be very different from what we see from Earth. Our night sky contains countless galaxies because we exist inside a populated region of the cosmic web. But deep inside a giant void, galaxies would be much farther apart. Bright structures would become rarer. Vast stretches of darkness would separate one concentration of matter from another. That image alone gives an idea of just how unusual these regions are. What makes the Bootes Void even more interesting is that scientists do not think it formed because matter was removed from the area. Instead, they think matter gradually moved away. This brings us to one of the leading formation theories. According to current models, the early universe was not perfectly smooth. Tiny differences in density existed shortly after the Big Bang. Some regions contained slightly more matter than others. The differences were incredibly small, yet gravity had billions of years to work with them. Regions that started slightly denser attracted more matter. As more matter gathered, their gravity became stronger. Stronger gravity attracted even more matter. Meanwhile, regions with slightly lower density gradually lost material to their denser neighbours. Over immense periods of time, this process amplified itself. Dense regions became denser, sparse regions became emptier, filaments formed, galaxy clusters formed, superclusters formed, and voids expanded. The Bootes void may represent one of the most dramatic examples of this process. Instead of matter collecting inside the region, matter slowly migrated towards surrounding structures over billions of years. Think of rainwater flowing across a landscape. Water naturally moves toward valleys and low points. Over time, the valleys collect more water while higher areas become drier. Something similar happens with matter in the universe, except gravity is doing the work over billions of years rather than hours or days. Matter flows toward denser regions. The denser regions grow, the emptier regions lose material. Eventually, enormous voids emerge. This process helps explain why the Bootes void exists without requiring any exotic physics or mysterious event. Yet even with this explanation, the sheer scale remains remarkable. The region is so large that it continues to attract attention decades after its discovery. Astronomers have spent years studying the galaxies that do exist within the void, because those galaxies may offer clues about how galaxy formation works in low-density environments. Life inside a void is very different from life inside a crowded galaxy cluster. Galaxies in dense regions frequently interact with neighbours. They collide, they merge, they distort one another through gravity. Gas can be stripped away. Star formation can be triggered. Entire galaxies can be transformed through these interactions. Inside a giant void, many of these events become much rarer. Galaxies can spend enormous periods of time relatively isolated from major encounters. That isolation makes them valuable to scientists because it allows researchers to study how galaxies evolve when external influences are minimized. The Bootes void therefore became more than just a giant empty region. It became a natural laboratory. Every galaxy found within it provides information about what happens when galaxies grow up in cosmic solitude rather than crowded environments. Another reason the void remains important is that it helps astronomers test simulations of the universe. Modern cosmology relies heavily on computer models. Scientists create simulations that begin shortly after the birth of the universe and then allow gravity, dark matter, and cosmic expansion to shape structures over billions of years. If the simulations are correct, they should naturally produce structures similar to those observed in reality. Voids like the Bootes void provide a powerful test. If simulations create voids that are too small, too large, too empty, or too crowded, then something may be missing from the model. The existence of giant voids therefore serves as a benchmark for understanding whether our theories accurately describe how the universe evolves. What makes this particularly interesting is that voids are sometimes easier to study theoretically than dense regions. Dense galaxy clusters contain countless complicated interactions: gas collisions, black hole activity, galaxy mergers, star formation, feedback from supernova explosions. All these processes create complexity. Voids, by comparison, are simpler environments. Their emptiness makes them useful for testing how matter behaves on large scales without so many competing influences. Even today, when astronomers create maps of the cosmic web, giant voids remain just as important as the filaments and clusters surrounding them. In some ways, understanding the universe requires understanding both the crowded regions and the empty ones. You cannot fully understand a web by only studying its threads. You also have to understand the spaces between them. The Bootes void revealed one of those spaces on a scale that few people imagined before its discovery. The South Pole Wall. The South Pole Wall is one of the most surprising discoveries in modern astronomy because it was not hidden at the edge of the observable universe. It was hidden much closer to us. For decades, astronomers mapped galaxies, built larger surveys, and created increasingly detailed pictures of the cosmos. They found galaxy clusters, superclusters, giant filaments, and enormous voids. It seemed like humanity was steadily completing the map of the nearby universe. Then, in 2020, astronomers announced the discovery of a structure stretching roughly 1.4 billion light-years across that had remained largely unnoticed. That is what makes the South Pole Wall so remarkable. A structure of this size sounds impossible to miss. After all, 1.4 billion light-years is an almost unimaginable distance. The Milky Way is about 100,000 light-years across, yet this structure extends across a region thousands of times larger. If something this massive existed, why did nobody recognize it sooner? The answer has less to do with the structure itself and more to do with our position inside the Milky Way. The discovery came from galaxy redshift surveys, which allow astronomers to build three-dimensional maps of the universe. Instead of simply showing where galaxies appear in the sky, these surveys reveal how far away galaxies are and how they move through space. As scientists analyzed the motions and positions of thousands of galaxies, they noticed that what appeared to be separate groups and clusters were actually connected pieces of a much larger structure. Slowly, a giant wall-like concentration of galaxies began to emerge from the data. The reason it stayed hidden for so long is because of something astronomers call the zone of avoidance. From our location inside the Milky Way, certain parts of the sky are difficult to observe because our galaxy is filled with stars, gas, and dust. These materials can block the view of distant galaxies located beyond them. In simple terms, our own galaxy gets in the way. Imagine trying to study a distant city while standing inside a dense forest. The buildings are still there, but the trees make them difficult to see. Astronomers face a similar problem when looking through the crowded plain of the Milky Way. For many years, this blind spot prevented a clear view of what existed beyond it. The South Pole Wall turned out to be one of the largest structures hidden behind this obstacle. Its discovery became possible because astronomers used more than ordinary visible light observations. They combined galaxy redshift data with infrared and radio observations. Infrared light can pass through dusty regions that block visible light, while radio observations can reveal galaxies that would otherwise remain hidden. Together, these techniques allowed researchers to look through regions of the sky that had acted like a curtain for decades. As more data became available, scientists realized they were not seeing isolated galaxy groups. They were seeing parts of an enormous interconnected structure, clusters linked to filaments, and filaments linked to even larger concentrations of galaxies. What once looked fragmented slowly revealed itself as a coherent wall extending across a huge section of the nearby universe. The South Pole Wall is part of what astronomers call the cosmic web. On the larger scales, galaxies are not spread evenly through space. Instead, they gather into a vast network of filaments, walls, and clusters, separated by enormous empty regions called voids. The universe resembles a giant interconnected structure where matter collects along dense pathways while large empty spaces lie in between. The South Pole Wall represents one of these dense concentrations. It formed over billions of years through the action of gravity. In the early universe, tiny differences in density existed from place to place. Some regions contained slightly more matter than others. Over time, gravity amplified those differences. Regions with more matter attracted even more material, growing larger and denser. Eventually, galaxies formed, then clusters, then superclusters, and finally immense structures like the South Pole Wall. The discovery is important for another reason. Astronomers do not just study where galaxies are located. They also study how galaxies move. The motions of galaxies reveal the influence of gravity across vast distances. By understanding where large concentrations of matter exist, scientists can better explain why galaxies move the way they do and how matter is distributed throughout the universe. What makes the South Pole Wall especially significant is that it reminds us how incomplete our cosmic map still is. Humanity has mapped millions of galaxies and developed powerful telescopes capable of studying the distant universe, yet a structure spanning 1.4 billion light-years remained hidden because our own galaxy blocked the view. The Phoenix Cluster. The Phoenix Cluster is one of those discoveries that immediately made astronomers rethink what they thought they already understood about galaxy clusters, because these systems are usually seen as well-studied massive structures that contain hundreds or even thousands of galaxies bound together by gravity, surrounded by huge amounts of hot gas and dark matter. And for a long time, scientists believed they had a fairly stable picture of how the centers of these clusters behave. That is why the discovery in 2010 came as such a surprise. It was first observed through X-ray data from the Chandra X-ray Observatory, which is designed to detect extremely hot and energetic gas in space. And when astronomers pointed it toward this cluster, they found something unusual happening right at the center that did not match normal expectations for a system of this size and age. In most galaxy clusters, the central region is filled with extremely hot gas reaching millions of degrees, and this gas gives off strong X-rays that can be measured from space. While this environment is extremely energetic, it is also usually stable in the sense that it does not produce large amounts of new stars, because the gas is expected to stay too hot to collapse easily under gravity. For many years, this idea held up across many different clusters, where star formation in the core was relatively low compared to what theoretical models once predicted. But the Phoenix cluster did not follow this pattern. At its center, astronomers found a galaxy producing stars at an extremely high rate, far higher than expected for a cluster core filled with such hot gas. Instead of being quiet or stable, the central region was active, with large amounts of material cooling and turning into new stars. This made the cluster stand out immediately, because it looked like a system where conditions that normally prevent star formation were not fully doing their job. The cluster itself is extremely massive, with a deep gravitational field holding together galaxies, hot gas and dark matter across a large region of space. At its core sits a huge reservoir of gas that emits strong X-ray radiation, which is what allowed Chandra to detect and study it in detail. The key surprise is that despite this hot, high-energy environment, enough of the gas appears to be cooling down to feed rapid star formation in the central galaxy. This process is known as a starburst, where a galaxy forms stars much faster than normal, and in the Phoenix cluster, this activity is unusually strong for a cluster core. In most models, something should be stopping or slowing this cooling process, often energy from black holes or heating from surrounding gas. But in this case, the balance seems weaker or less effective, allowing star formation to continue at a much higher level than expected. This is why the Phoenix cluster became so important. It showed that even in environments thought to be well understood, there are still extreme cases that do not fit the usual rules. It also highlighted how important X-ray astronomy is for studying galaxy clusters, because without X-ray observations, the hot gas and the extreme conditions at the center would not be visible in the same way, and the unusual behavior might have been missed. Cosmic Web Filament Networks. The Cosmic Web Filament Network is not a single object in space, but a connected structure that describes how almost everything in the universe is arranged on the largest scales. And the idea behind it slowly developed over decades as astronomers realized that galaxies are not spread randomly through space, but instead form a huge interconnected pattern that stretches across the observable universe. The early hints of this structure began in the 1970s, when galaxy surveys started becoming large enough to show that galaxies tended to group together rather than spread evenly, and instead of being randomly scattered, they appeared in clusters, with large empty spaces between them. But at that time, the data was still limited, so scientists could only guess at the full structure behind what they were seeing. As technology improved, especially with redshift surveys, astronomers were able to measure not only where galaxies appeared in the sky, but also how far away they were. And this allowed them to build three-dimensional maps of the universe, which revealed something much larger and more structured than expected. Because galaxies were not just forming clusters, they were forming long connected chains that stretched across huge distances. These chains are called filaments, and they act like bridges between massive galaxy clusters, which sit at the intersections of these filaments like nodes in a vast cosmic network. And when enough data was collected, it became clear that these filaments were not isolated features, but part of a much larger system that links almost every known structure in the universe. Some filaments span hundreds of millions of light years, and they can connect superclusters together, forming continuous threads of matter that define the large-scale shape of the universe. And even though these structures are extremely large, they are still made up of galaxies, gas, and dark matter distributed along long stretched-out regions rather than solid continuous matter. This is why the term cosmic web is used, Because the structure resembles a vast network where dense regions form the knots and long filaments form the threads, while empty voids fill the spaces in between. And this pattern is now considered one of the most important discoveries in modern cosmology, because it explains how matter organizes itself across the universe. The structure was not discovered all at once, but gradually built up through years of observation, combined with computer simulations, where scientists used large-scale models like the Millennium Simulation and Illustris to recreate how the universe might evolve from its early state into the present-day distribution of galaxies. And what they found was that when dark matter and gravity are included in the models, filament-like structures naturally form over time. This agreement between simulations and real observations was one of the strongest pieces of evidence supporting the idea that the cosmic web is the correct description of large-scale structure, because both real data from surveys and simulated universes produce similar patterns of filaments, clusters, and voids, suggesting that the same physical processes are shaping the universe on the largest scales. However, the cosmic web is not something that can be fully observed directly in a single image or map, because it exists across enormous distances and requires combining data from millions of galaxies, and even then, parts of it remain uncertain due to limitations in observation and measurement. Redshift surveys are essential for building these maps, but they also introduce challenges, because measuring distance in the universe relies on interpreting how light shifts due to cosmic expansion, and small uncertainties in redshift measurements can affect how filaments are connected in large-scale reconstructions, especially when dealing with structures that span hundreds of millions of light-years. Despite these challenges, the cosmic web framework has become the standard way of understanding how matter is distributed across the universe, and it is now recognized as the largest known connected structure system, linking galaxies, clusters, and superclusters into a single, vast network. Even with this understanding, the study of large-scale structure is still far from complete, and new surveys continue to refine how these filaments are mapped and connected, because every improvement in telescope technology reveals more detail about how the cosmic web is arranged. This leads to the closing idea that the universe is still being measured. One of the most important reasons for this is that even the largest telescopes have limits, because they can only observe within the observable universe, meaning the region from which light has had time to reach us since the beginning of cosmic expansion. And anything beyond that remains inaccessible, no matter how advanced our instruments become. There are also distortions caused by redshift measurements, where the expansion of the universe affects how distances are calculated, and this can make structures appear stretched or compressed, depending on how their motion and position are interpreted, which adds uncertainty when mapping extremely large filaments. Another limitation comes from dark matter, which makes up most of the mass in the universe but cannot be observed directly, meaning its distribution must be inferred through gravitational effects rather than direct detection. And this adds another layer of uncertainty when reconstructing the cosmic web. Even with these limitations, new tools are being developed that will significantly improve our understanding of large-scale structure, including the Vera Rubin Observatory, which will scan the sky in unprecedented detail, and the Square Kilometre Array, which will use radio signals to map galaxies and cosmic hydrogen across vast distances. Each of these tools will add more detail to the cosmic map, revealing finer filaments, deeper structures, and possibly even new large-scale patterns that are currently unknown. And as these future observations come in, the cosmic web will continue to evolve as a map, not because the universe is changing in a way we can see directly on human timescales, but because our understanding of it is still growing, and every new survey adds another layer to the structure of everything we can observe in space.